Well, hi there, students. Welcome back. Today we're going to continue learning some rules for finding derivatives, kind of our shortcut rules. And today's is called the product rule, and we're on notes number 20. So you don't need to write what you see me do on this particular slide. What I want to do is explore some what-ifs. So let's say I have this function y equals x squared plus 1 times 3x minus x cubed, and I want to find the derivative dy dx. So I'm going to do something that I don't know if it will work, and then I'm going to do something that I know will work. So this is going to be a guess. Can I just find the derivative of the first part and find the derivative of the second part and multiply them together? Let's see. Dy dx would be, so the derivative of the first part would be 2x plus 0, or just 2x, because the derivative of x squared is 2x and the derivative of 1 is 0. And when we have a sum, we just add the two derivatives together. And then the derivative of the second part would be 3 minus 3x squared, because the derivative of 3x is 3 and the derivative of x cubed is 3x squared, and we would subtract those. And then if we want to simplify this answer, we have 6x minus 6x cubed. So we don't know if that is right. But that's just a hunch, like why not just multiply the derivatives of the two parts together? So now let me do something that I know is mathematically correct, and we'll compare the answer with the guess. So this is mathematically correct. We can rewrite the function y by using the FOIL technique, and when we multiply the firsts we have 3x cubed. When we multiply the outsides we have minus x to the fifth. When we multiply the insides we have plus 3x, and when we multiply the lasts we have minus x cubed. Okay, so then we could combine the like terms. So we have y equals 2x cubed minus x to the fifth plus 3x, and now we can find the derivative. By the way, dy dx is the official Leibniz notation, and f prime of x is the official Newton notation, but a lot of times with y, we're just going to kind of do a fusion of the two notations and call it y prime, because that's so much simpler. So the derivative y prime would be, let's take the derivative of the first term, and that would be 6x squared, minus the derivative of the second term would be 5x to the fourth, plus the derivative of the third term would be 3. And clearly that is not equal to the other one, so the first way must not have been right. So apparently you cannot find a derivative by just multiplying the derivatives of two products. Or excuse me, I should say that. You can't find the derivative of a product by multiplying the separate derivatives together of the two parts. So if you can't do that, you might run across some problems that you can't just FOIL. Not everything is FOILable. So we are going to come up with a rule that does work for all products. That's the goal of today's lesson. And to come up with a rule, often what we do is we algebraically derive the rule from something else. Now, the process of algebraically deriving this rule is not something I would expect you to be able to come up with yourself, but I do want to show you the process, and I think you'll recognize the parts, and we're just going to quickly look through it. So what we're trying to do is find the derivative of a product. So I'm writing my product as f times g, and the prime symbol is the derivative symbol. Okay. So that means what we're trying to do is find the limit of the slope of the secant line, right? Because that would give you the slope of the tangent line. And so we have the limit of the function evaluated at x plus h minus the function evaluated at x over h, and we have the limit as h goes to 0. So that's one of our two limit definitions. And when you see f times g of x minus h, it just means f of x minus h times g of x minus h. And when you see f times g of x, it just means f of x times g of x. So I just changed the notation to something a little bit more familiar. Now, here comes the interesting part of this proof. What we do is we break up those numerator terms and we insert something in between. Now, to keep an expression equivalent to what it originally was, you can't just add anything. Just like if you're going to multiply an expression by something and you want to maintain its value, you can multiply by 1 or a special form of 1. Well, if you want to add something to an expression and you want to maintain its value, you would have to add 0 or a special form of 0. So that's what you're going to see right here. Oops. You're going to see that I'm about to add a special form of 0. Notice that the two terms are opposites. You have minus f of x, g of x plus h, and plus f of x, g of x plus h. So I really just added 0. And you'll see why that was chosen here as we go through. In the next step, what I've done is just break this fraction that had 4 terms in the numerator into 2 fractions that each have 2 terms in the numerator. So these first 2 numerator terms went into the first fraction, and these last 2 numerator terms, still over h, went into the last fraction. Okay, next we look at each one separately and we notice that you can factor g of x plus h out of both terms in the numerator there, and you can factor f of x out of both terms in the numerator there. And I hope you're not writing this down. I should have said that at the beginning. Please don't write this down. Just watch. Okay, so I've factored those things out. Now we have some limit laws, which were the rules about how you can work with limits and split them up. And we just glossed over those at the beginning of the year. We didn't spend a lot of time, so you'll have to take my word for it on the next step. It's not letting me use that tool. There we go. You can ignore those yellow dots. So the limit of this product can be broken down into the limit of the first factor times the limit of the second factor. And the limit of this product can be broken down into limit of the first times the limit of the second. So you can split up a limit like that. Not a derivative. You can't just do the derivative of the first and the derivative of the second. But limits and derivatives are not the same thing. Limits are involved in derivatives, but a limit and a derivative are different things. Now, let's evaluate these limits. Look at the first one. If you put 0 in for h, you just get g of x. Look at the second one. This is a definition of f prime of x. Look at the third one. There's no place to put the 0 for h, so you just get f of x. And look at the fourth one. This is the definition of g prime of x, the derivative of g. So that means we have g of x times f prime of x plus f of x times g prime of x. Remember, g was the first, f was the first function in our product, and g was the second function in our product. And typically we rearrange these a little bit. We write f times g prime plus g times f prime. So that is our new rule. It's called the product rule, and it's for finding the derivative of a product. So in this formula, our product is f times g. F is the first factor, g is the second factor. We usually just call them the first and the second. And what you do is you take the first times the derivative of the second plus the second times the derivative of the first. And in fact, I would say that to myself over and over as I'm memorizing this rule. The first times the derivative of the second plus the second times the derivative of the first. The first times the derivative of the second plus the second times the derivative of the first. And then for your Leibniz notation, for all of you Leibniz fans out there, u times v is the product. So u is the first, v is the second, and we see again the first times the derivative of the second. The derivative of v is dv dx, plus the second times the derivative of the first. The derivative of u is du dx. So no matter how you write it, it's the first times the derivative of the second plus the second times the derivative of the first. Now let's do some examples. So this was the problem I was playing with in the beginning. Oh, by the way, hopefully you realized you should write this down. This is where you start taking notes. Okay, now you can also take notes on the examples. So let's use the product rule to find the derivative of this function, and we'll compare it to the answer we got when we did it the mathematically correct way. So y prime is going to be the first x squared plus 1 times the derivative of the second. Okay, the derivative of 3x minus x cubed is 3 minus 3x squared, plus the second, 3x minus x cubed, times the derivative of the first, 2x. Does that answer look like the answer I got way back in the beginning? Well, no, not exactly, but that's because we haven't simplified our answer yet. So this is not the best problem to use the product rule on because there's so much simplifying to do. It would have just been easier to FOIL first and then differentiate after, but I needed to do it this way because this is one kind of example that we can show two ways. So I'm going to go ahead and FOIL. And then on the other part, I'm going to distribute the 2x. And then let's see what like terms we might have to combine. It's looking like we've got some that can cancel and a couple that can combine. So then I have negative 5x to the fourth plus 6x squared plus 3. Is that what I had before? Yep, I didn't have it in exactly the same order, but that's okay. It is the same thing. Cool. Okay, so there are some problems that you won't be able to do by simplifying the function first, and you'll have to use the product rule, and the product rule will be the better choice and the more efficient choice. For example, number 2. Here's y equals x cubed times e to the x. Let's find the derivative. Notice there's nothing we could do to simplify this function even if we wanted to. So all we have is a product. X cubed is the first, e to the x is the second. The derivative is going to be the first, x cubed, times the derivative of the second. Do you remember what the derivative of e to the x is? It's e to the x, plus the second, e to the x, times the derivative of the first, and the derivative of x cubed is 3x squared. Now there is a little bit of simplifying we could do to this. We don't need those dots in there, and we usually put the number coefficient first. I'm just going to write it as x cubed e to the x plus 3x squared e to the x. Now an optional step would be to factor. You don't have to factor to simplify an answer, but we will get into some kinds of problems where factoring helps us solve the problem. It'll have more sorts of steps. So if you did want to factor, you could factor x squared out of both terms, and you could factor e to the x out of both terms, and that would leave you with x plus 3 as your other term. So that's an equivalent answer. Okay, now let's take a look at number 3. And this is one where we could, I suppose, FOIL first, but I'm not going to. I'm just going to go ahead and use the product rule first. So the derivative is the first, 2x to the fourth minus 1, times the derivative of the second, and the derivative of e to the x is e to the x, and the derivative of 1 is 0, so that part is just e to the x, plus the second, e to the x plus 1, times the derivative of the first, and the derivative of 2x to the fourth is 8x cubed, and the derivative of minus 1 is 0. Okay, so we have the derivative. Let's go ahead and simplify. So I'm going to distribute e to the x, and I get 2x to the fourth e to the x minus e to the x, and then I'm going to distribute the 8x cubed, so I get plus 8x cubed e to the x plus 8x cubed. And it doesn't look like any of those terms are like terms, so that's our answer. All right. Now, the product rule that we've seen so far was just applied when you have two factors, like f times g, a first times a second. But you can extend the product rule to 3 or more factors. I'm not going to prove it, but it looks like this. The derivative of a product of 3 parts, or 3 factors, is the first times the second times the derivative of the third plus the first times the derivative of the second times the third plus the derivative of the first times the second times the third. And hopefully you realize that the order I put these in doesn't matter, but what you notice is that there are 3 terms, and each term has the derivative of one part, and then the other 2 parts just their normal functions. You could extend that to 4, 5, etc. Each time you'll have that many terms, and you'll have one derivative in that part, and then the rest are the normal function. So let's try that with problem number 4. Notice I have a first, a second, and a third. And I suppose I could first simplify the problem and multiply the x by the 2x minus 1, and then it would not be a product of 3 factors anymore. That's totally fine. You have multiple ways of doing these problems. But what I'm going to do is demonstrate the extended product rule for 3 factors. So we have the first, x, times the second, 2x minus 1, times the derivative of the third, e to the x, plus the first, x, times the derivative of the second, 2, times the third, e to the x, plus the derivative of the first, which would be 1, times the second, 2x minus 1, times the derivative, or excuse me, times the third, e to the x. So the e to the x was a derivative in the first one, the 2 was a derivative in the second one, and the 1 was a derivative in the third one. And then from there, you could multiply it all out and combine like terms, but I think for now I'm just going to leave it because I know this video is getting a little long, and I don't think that's the main point of the problem. Let's take a look at number 5, which doesn't look like a product of terms, but it's something that we don't know how to differentiate. See, we know how to differentiate f of x equals e to the x, but that only applies to e to the x. It doesn't apply to e to the 3x. So we need a way to change how this function looks, and maybe we can change it into something that looks like something we have a rule for. So keep in mind that e to the 3x means e to the x times e to the x times e to the x. You add the exponents, x plus x plus x is 3x. So I can think of this as a product of 3 factors and use the extended product rule to find the derivative. Each time I'm going to have the derivative of one of those 3. So we have the first times the second times the derivative of the third, plus the first times the derivative of the second times the third, plus the derivative of the first times the second times the third. Wow. Together we have 3 of these things, And remember, e to the x times e to the x times e to the x is e to the 3x. So the derivative of e to the 3x is 3e to the 3x. Let's go out on a limb. What do you suppose the derivative of e to the 4x would be? Can you see yourself splitting that into e to the x times e to the x times e to the x times e to the x, and each time you're going to have the derivative of one of them, and then the other three are normal, and you have 4 of those? The derivative would be 4e to the 4x. Now we're going to come back to this idea when we get to a rule that has to do with having a function inside a function. So for now, we're just kind of playing around with it. Okay, we're going to wrap this up with just a little bit more. So in numbers 6 and 7, we're not given a function and asked for its derivative, but we're still applying the rules to the situation. So number 6 gives us f of 3 and g of 3 and f prime of 3 and g prime of 3. And in part A, we're asked to find the derivative of f plus g. Well, remember from last time, the derivative of a sum is the sum of the derivatives. In other words, you can just take the derivative of the first and add the derivative of the second. That's okay with addition, and that's okay with subtraction. So that means we have negative 6 plus 5. So our answer is negative 1. However, when we look at part B, we're asked to find the derivative of the product. And the whole point of today's lesson is that the derivative of a product is not the product of the derivatives. The derivative of the product is found by using the product rule. And according to the product rule, we take the first times the derivative of the second plus the second times the derivative of the first. Once we have that established, let's look back up at the top and plug in the numbers. So we have 4 times 5 plus 2 times negative 6. 20 minus 12 is 8. Okay, and then number 7 is kind of a blend of this last problem we did and the previous problems, because we have a function which is a product. X squared is the first, f of x is the second, so we do know half of it and we don't know half of it. So to find the derivative, dy dx, or y prime if you want to call it that, you're going to use the product rule. The first, x squared, times the derivative of the second, well, we're just going to have to call that f prime of x because we don't know what f of x is, plus the second, f of x, times the derivative of the first. We do know the derivative of x squared is 2x. So if I rewrite this, I'm just going to put the 2x before the f of x. It's a halfway known answer, halfway unknown answer. And that's fine. All right. Let's wrap it up with some concept check questions. True or false? Is the derivative of the product f times g just the same as the derivative of f times the derivative of g? What do you think? You're right, that is false. The derivative of a product is not the product of the derivatives. That's the whole point of today's lesson. Is the derivative of the product the first times the derivative of the second minus the second times the derivative of the first? You're right again. That is false. The problem was the minus. It's supposed to be plus. Is the derivative of a product the second times the derivative of the first plus the first times the derivative of the second? Oh, I see. I tricked some of you. See, it doesn't matter when you're adding what order you put the terms in. So this could be first or second. This could be first or second. The first times the derivative of the second plus the second times the derivative of the first. It means the same thing. So that is equivalent to the product rule. If you want to go with that form of the product rule, you can. Next time when we learn the quotient rule, you might decide that you like your product rule this way. Is this the product rule? The first times the derivative of the second plus the second times the derivative of the first? Yes, you're right again. That is true. And is this true? The derivative of the product evaluated at 4 would be f of 4 times g prime of 4 plus g of 4 times f prime of 4. You got it. Boy, I think you got all of those. That's true as well. We just put the 4 in for x in all of those places. Very good. Okay, here's your assignment. And you know how in the lesson there was at least one problem that we could do a couple of different ways, and maybe one way takes longer and is more complicated than the other? Well, that's going to happen on your assignment from the book as well. And so what I thought I would do is give you some bonus footage and take a look with you at number 21 and 29. So if you don't want to, you can just go ahead and do your homework, but you might run into some issues when you get to those. I'm going to go ahead and keep running and take a look at those problems with you. So 21. And the directions say calculate the derivative. So it's not a bad idea to stop and look at what you're doing and think for a minute. Believe it or not, stopping to think is a good thing. I'm going to show you how to do this 2 different ways. Hopefully we'll get the same answer both ways. But I'm feeling like because we have conjugates here, we could simplify our function first. What if we multiply these out? First gives us x, the inside and the outside cancel, and the last gives us -1. And now if we take the derivative, find the derivative, take the derivative, it kind of means the same thing. We just get 1. The derivative of x is 1, and the derivative of -1 is 0. Now, suppose instead we use the product rule. Going back to the original function. So we have the first. Now, actually, I'm going to think of it as x to the 1/2 plus 1 times x to the 1/2 minus 1, because when I'm differentiating, I like to use the power rule, so I need those powers there. So we have the first times the derivative of the second, and the derivative of x to the 1/2 is 1/2 x to the -1/2, and the derivative of -1 is 0. Plus the second times the derivative of the first. Again, the derivative of x to the 1/2 is 1/2 x to the -1/2, and the derivative of +1 is 0. Now, to simplify this, what I'm going to do is distribute. And when I multiply 1/2 x to the -1/2 by x to the +1/2, I need to add the powers on x. So we get 1/2 times x to the 0. X to the 0 is just 1, so that is just 1/2. Plus 1/2 x to the -1/2 from doing the second part. So we did the first part, the second part, and then we're going to also distribute for the second half of the problem. And again, we get 1/2 minus, and then for the second part, 1/2 x to the -1/2. So we have 1/2 plus 1/2, which is 1. And then we have 2 terms that are opposites, and they cancel. So doing it the first way was much simpler than doing it the second way, but they both can lead you to the same answer if you don't get lost in the woods. Let's look at number 29. Okay, again, the directions are to calculate the derivative. So we have f of t equals 3 to the 1/2 times 5 to the 1/2. Stop and think. You might be so gung-ho to use the product rule that you're like, okay, I have a product. I'm going to use the product rule. Let's go. But where is the t? On this right side, where is the t? There's no t. 3 to the 1/2 is just a constant. 5 to the 1/2 is just a constant. A constant times a constant is a constant. This is just a constant. And what's the derivative of a constant? 0. So f prime of t is 0. Now, if I was using the product rule, it would look like this. The first, 3 to the 1/2, times the derivative of the second. Well, the derivative of a constant is 0, plus the second times the derivative of the first, and again, the derivative of a constant is 0. 0 plus 0 is 0. Luckily, that didn't take a whole lot of time, but it was really unnecessary to do that. Okay, thanks everybody.